metallicity over cosmic time, we can learn about how quickly and how slowly these galaxies have quenched on average. And finally, we can learn about galaxy assembly. And the reason for this is that quiescent galaxies, by definition, they're no longer forming stars. And so their chemical composition is not going to change. It's like locked in place at the time of quenching. And so this shouldn't evolve over time. And by comparing the quiescent galaxy population since higher redshift to today, we can learn about, and if it's different, we can learn about what maybe caused that difference. For example, you can change the chemical composition of these galaxies by adding new stars to their halos through mergers, accretion of stars, or also late-time mergers. So we want to be doing some comparison to the lower redshift universe. So what do we find today in today's universe for these massive quiescent galaxies? So right here I'm showing average of hundreds of galaxies for each data point from SDSS. And I'm looking at the stellar compositions. This is not gas phase. And these are quiescent galaxies. And the first thing we find is that galaxies with larger velocity dispersions, they're more metal rich. This is essentially the stellar mass metallicity relation. The second thing is we find that these galaxies at higher velocity dispersions, they have enhanced alpha abundances, this ratio of alpha to iron. This ratio probes the star formation timescale of a galaxy because it's looking at the ratio between enrichment of core collapse and type 1a supernova. So this correlation that we find is essentially a correlation with star formation timescale, where in galaxies with larger dispersions, they form their stars over shorter timescales. And when we combine this result with the final panel that these galaxies are also older, we can put together a picture of galaxy formation in which galaxies with larger stellar masses form their stars earlier and over shorter timescales than lower mass galaxies. But this story is kind of incomplete because we're trying to understand galaxies that quenched like 10 billion years ago. And it's hard to imagine that their stellar populations haven't changed over cosmic time, like I said, through mergers or late-time star formation. So by going to higher redshift, we can see, is this picture still the case? Does this hold up at higher redshift? And also, we can learn about how if these relations change over cosmic time, we can learn about the assembly of the galaxies since redshift 2, or higher. Okay, so let's go to higher redshift. It sounds like that's the right thing to do. How about a redshift greater than 1? Haha, psych, just kidding. We actually don't know what these relations look like at higher redshift. Kind of a silly plot. But the reason for this, and you're like, oh, redshift 2, that's so low. Redshift 1, that's so low. But actually, this is really hard to make these measurements. And to demonstrate why that is, here is a simulation of 2 galaxies of the same stellar mass, one star forming and one quiescent. And you can see for the star-forming galaxies, you have these booming emission lines from which you can measure metallicities. For the quiescent galaxies, though, you probably can't even see, but there's these teeny tiny wiggles in the stellar continuum. We don't have these emission lines. So you need really high single-to-noise spectra. And not only that, but when we blow up this spectrum, what you see is it's super complicated. So we're trying to measure these individual absorption features, but they're also blended with nearby absorption features. So we both need good models, and we need high signal-to-noise data. For that reason, the mass metallicity relation, one of the more simple relations, has not been measured out to a redshift past 0.7. We're hoping to push this to higher redshift. So these are the surveys that are actually going to take us there. I'm showing as a function of redshift. I just presented on SDSS. And before I get to these exciting higher redshift surveys, I want to briefly touch on the legacy survey, which is at a redshift of around 0.7. And it was a survey of around 4,000 massive galaxies. It was an ultra-deep spectroscopic survey conducted with VMOS on the VLT. And I selected 135 quiescent galaxies that cover a range of important optical absorption features. And to show you how powerful these 135 galaxies are in their spectra, I've binned them by velocity dispersion, and I stacked their spectra. And I just want to show you how amazing these spectra look. Here are the 4 spectra in bins of dispersion that each have around 30 galaxies in them. And what you can see is it's extremely clean. All of these wiggles are real. They're caused by metals of the absorption that are being absorbed in the atmospheres of stars. The other thing you might want to notice is that this is really hard. Like the difference between each spectrum here, we expect to find these relations as a function of velocity dispersion. It's really subtle. So you can only pick out some of these differences in the spectra once you take the difference. So for example, the Balmer lines get deeper and other metal lines get shallower. So the legacy spectra are super powerful. Something that we can do with all of this data is we can, as a teaser, I'm not going to get into all of it, but we've actually measured the abundance ratio or elemental abundances for 11 elements. And I've separated them here by their enrichment timescales, or enrichment. So here I have, it's kind of not showing up, but here I have the light elements, the alpha elements, and the iron peak elements. And you can also take a look at the abundance ratios. So it's really information-rich data, and I refer to my 2023 paper for more information about how we can use this information to interpret things about these galaxies and their past chemical enrichment. Okay, but a limitation of the legacy survey is we're trying to study quiescent galaxies at a time in the universe where most massive galaxies have already become quiescent. So we want to push to even higher redshift, where we can study the population when it was smaller and likely very different. So the heavy metal survey allows us to do just that. It's a Keck survey that Mariska, my advisor, she was the one that started it, and it was ongoing when I got here. Actually, my first year, they're like, you're going to get to figure out all the results for this exciting new survey, and then we were wintered out for many years, so I'm finally getting to look at the exciting results. But we have 11 quiescent galaxies at redshift 1.4 and 10 at redshift 2.1. And in order to get the high signal noise we need at this high redshift, we had to observe every galaxy for 30 hours on Keck, which is a big ask. That was split across 2 different filters from Aliza and Mossfire. And here are example spectra. So at top, I'm showing redshift 1.4, and at bottom, I'm showing redshift 2.1. And on top, I'm showing the best fit model. I did a full spectrum modeling to get the elemental abundances. And I assumed variable alpha abundances for this. And you can see that the model follows really well. And we're actually picking up these absorption features that were hard to even see at redshift below 1 not too long ago. So prior to the heavy metal survey, here was the situation. Again, I'm showing the similar plots from the beginning. I have velocity dispersion on the x-axis and abundances on the y-axis. And I'm showing the SDSS results that I showed earlier in black, and then the dashed is legacy. And prior to heavy metal, we only had 2 measurements at redshift 2. One of them was a lensed galaxy way up there. It looks kind of strange, it's way up there. The other 3 were lensed galaxies and a stack of thousands of galaxies. So we didn't know a lot at this point. But now with the heavy metal survey, we're starting to fill in this parameter space. I will note that these are large uncertainties, but this is just the start. We're making slow progress. Actually quick now. We tripled the number of galaxies at this redshift. And essentially what we're starting to see is that these galaxies at higher redshift, quiescent massive galaxies, are iron deficient. They're slightly alpha enhanced. And they formed extremely early, and they quenched by redshift 4 at higher redshift. And that kind of follows. It's easy to understand because we have a selection limit based on the age of the universe at the time of quenching. But to understand this evolution a little bit better, I'm going to reproject it. So the x-axis is now going to be redshift, and I'm just going to take the average at each redshift so we can see how things change over time. Oh, I did also want to mention that we measured a mass metallicity relation, but sample sizes are small, so who knows. But as it stands, it does have the same slope as the lower redshift samples, just offset to lower values. Okay, so here are the averages as a function of redshift. And remember what I said is that the magnesium over iron ratio tells us something about the star formation timescale of galaxies. So using that and comparing it to simple chemical evolution models, we can come up with a story where galaxies at higher redshift, they formed in these extremely short bursts and quenched rapidly very early in the universe, and at later times, galaxies with progressively long star formation timescales quenched and were added to the population. So the average has decreased over time. So let's try to understand this a little more. How does this evolution occur? It's pretty drastic. It's striking how short these star formation timescales are for the high redshift sample. A question that falls out of this is, do these chemically extreme galaxies persist as rare remnants in the lower redshift universe? If they do, that might imply that the quiescent galaxy population is just growing rapidly. We know from the stellar mass function of quiescent galaxies that the population has grown an order of magnitude at these masses. And so you can imagine that if you add quiescent galaxies to the population, this is also known as progenitor bias, that at later times, those galaxies might have larger iron abundances. They formed over longer timescales. They're going to have lower magnesium over iron. The average is going to decrease over time. And you would still have these heavy metal galaxies persisting. They'd be rare, but they would still persist in today's universe. The other way that this evolution can be explained is through growth of individual galaxies. You can imagine if the galaxies at redshift 2 are doing quite a lot of merging, and the galaxies they're merging with have different abundances, then their average stellar populations are going to change. They're going to have, the individual galaxies are going to have different chemical compositions by today. So we can look at the individual galaxies in today's, like the distribution of galaxies in today's universe. We can hunt for these rare, chemically extreme remnants in the lower redshift universe. So we have done this. I'm showing 2 comparison samples in the lower redshift universe. I'm showing the massive cores. So these are like 40 of the most massive galaxies within 100 megaparsecs, and the cores of those galaxies. And I'm also showing SDSS. And a lot of people think that possibly these galaxies are going to end up as the cores of the massive galaxies. And here are our galaxies. So the heavy metal are very chemically different than the massive galaxies. They're also 6 times less massive, so it's very unlikely that these will grow into the massive type galaxies by today's universe. The other striking thing is that there's a huge population of galaxies. Again, I'll mention error bars are large. This is preliminary, but we do find very iron-deficient galaxies that are not matched by today's massive quiescent galaxies. Same with the magnesium over iron, especially for the redshift 2 sample. They have to dramatically change their abundances in order to match the sequence of today. So it appears that mergers or late-time star formation is required to alter their individual elemental abundances. So again, the caveat of this whole work is that we have small sample sizes, large error bars, and so what we need to do is really increase the number of galaxies we have at this redshift to confirm this picture. And one way to do that is with the telescope everyone's been talking about, JWST. So I'm lucky enough to be a co-PI of a Cycle 1 JWST proposal with my advisor, and we are targeting 16 more massive quiescent galaxies at similar redshifts, but we're going to even lower masses, so we can maybe start to fill in the lower mass regime and get a better mass metallicity relation out of this. And we were able to find one pointing in which we were able to fit all 16 massive quiescent galaxies in near spec in the MSA, and we're going to stare at it for 16 hours. And I did some simulations just to see how good are these spectra going to be. It helped our proposal. So I simulated a spectrum for one of our fainter objects for 52 hours on Mossfire. And this is what it looked like, and I also compared it to 16 hours on near spec. And you can just see the individual absorption features here aren't just noise peaks. They're actual absorption features that we can model and get chemical abundances from. So I'm really excited. This data set is going to be amazing. I can't wait to get my hands on it. We've been waiting a while, but it looks like we're going to get it in around November, December time. So I can't wait to see what the parameter space looks like after all of this. So I hope I convinced you that it's an exciting time for stellar metallicities, and that there's a lot we can learn from studying the metals, especially stellar metallicities of massive quiescent galaxies. Thank you.
Is that like a protocluster or something? Is it actually or is it with the 16 galaxies all in one?
Well, so they range from redshift 1 to 2.5 within this one.
Oh, okay.
So some of them are really nearby, likely, but we only have photometric redshifts.
Right.
So going to those galaxies that are very, very high in stellar mass but low in iron to hydrogen, by what amount of stellar mass do you have to add with enhanced iron to hydrogen in order to boost those into the population? And it seems as though all of those galaxies in the local universe with that are in that trend of iron to hydrogen at about, I don't know, 0.1, you would have to have some constraint, I would think, on the likelihood that the stellar mass would have to be enriched by some iron-enhanced population in order to prevent, any galaxies at low redshift from being where your point at minus 0.2 is. So do you have a first order explanation of that? It seems very hard.
Yeah, it's pretty low. I will say the error bars are pretty large, but yeah, we're finding these very low iron galaxies, and I've had a hard time imagining, through mergers, especially people with minor mergers, you can actually grow the galaxy by a factor of 2 in stellar mass. And if you had mostly iron-rich galaxies, which maybe means that they had longer star formation timescales, more type 1a enrichment, they could do that. But also, minor mergers don't have very high, they're small. They're going to have low metallicity, and so you need major mergers to do this. But that's not very common. So we're struggling to understand how you can explain this.
Next speaker, please sit up.
Just a quick comment on that question is that it might be aperture effects, that if you have major mergers and you spread you concentrate the new metal rich stars in the central regions where people are measuring the iron, that could help. But my other question was about people studying massive compact, they call relic galaxies in the local universe. Do those match these abundance patterns of these high redshift ones you're looking at?
I actually don't know. That would be a great thing to look into. Yeah. I am wondering, we have a very small comparison sample right now of the lower redshift of individual measurements, and so you need pretty broad spectral range and also high signal to noise. And so I think by also increasing that, we might find these rare relics possibly in the lower redshift universe. Yeah.
Let's see whether this is working. Great. Okay, thank you.
Now we have Andy Burkert talking about self-regulated galaxy evolution from the origin of the universe.
No, this is self-regulating. But it's not on here. It's a challenge for you.
Sorry.
Don't. It's something close to the chaos. Close to chaos. Don't forget. Just forget about it.
Yeah.
Self-regulated galaxy evolution at the edge of chaos. Thank you. I'm sorry. No, I just wanted to start with